We will see later how the quantum electrodynamic Lagrangian arise by requiring to have gauge invariance. But for now, let's get the interaction part of the QED Lagrangian by analogy with the Yukawa Lagrangian. In the Yukawa theory, the interaction between the fermions is mediated by the scalar field. In QED, however, this scalar field has to be replaced by a vector field. However, this introduces a Lorentz index which we need to contract in order to get a scalar. This can be done by inserting the gamma matrix between psi bar and psi. Indeed, gamma is a 4x4 matrix, and psi bar is like a line spinor, and psi is a column spinor, so the only possibility to get a number out of it is to insert the matrix in between. The Feynman rules are the same as usual. For the Yukawa theory, we have three fields for the interaction part of the Lagrangian. Therefore, we have three lines connected by the vertex. The value of the vertex is minus ig, which g is a coupling constant. We have two fermionic lines because we have two fermionic fields, psi bar and psi, so one with an arrow pointing toward the vertex and one with an arrow pointing out toward the vertex. And for the bosonic field, we just draw it with a dashed line. For QED, the rules are more or less the same, except that now we have to change the bosonic line, the scalar bosonic line, by a vector bosonic line, and also the value of the vertex changes in order to account for the gamma mu matrix. Of course, the main difference between the QED and Yukawa theories is that the mediator of the interaction in QED has a spin 1. As a result, it can change the projection of the spin for the incoming and outgoing fermions. Therefore, in QED, in addition to the usual 4 momentum, we will associate to each fermionic line spinor, which will tell us if the particle is, for instance, in spin up, spin down, or if the antiparticle is spin up or spin down. The incoming and outgoing fermionic lines are on mass shell. And because we consider incoming and outgoing particles with a well-defined energy momentum for vectors, it's easier to use the Dirac equation in momentum space. Positive frequency solution, noted U, are for particles, and negative frequency, noted V, are for antiparticles. In both cases, the spinors are function of the 4 momenta k and the spin s. These u's and v's are easily expressed in the rest frame, and in order to get u of k or v of k, we can then boost the spinors. These expressions are only valid in the Dirac representation, which is a particular choice of the gamma matrices, and for which the expression of the spinors are convenient in the rest frame. The square root of m is just a normalization. To ensure that the amplitude gives us a number, we need to place the u, u bar, v and v bar in a particular way around the vertices. The u's and v's are a column spinor, therefore they need to be on the right-hand side of the gamma matrices. And similarly, the u bars and v bars are line spinors, so they need to be on the left-hand side of gamma. Also, we get a u or a v whenever the arrow on the fermionic line points toward the vertex. And similarly, we get a u bar and a v bar when the arrow points outward the vertex. Remember also that time runs from left to right, and therefore when the arrows of the fermionic line runs in the same direction as time, we have a particle which is described by u or by u bar. When they are opposites, we have an antiparticle described by v and v bar. For example, we can apply these rules to this vertex.